Okay, okay, Richard. So if you are ready, we may start.
Yeah, yeah, I'm ready.
Okay, so it's my pleasure to introduce Richard Bamler from University of Berkeley, and he will talk essentially on some beautiful new results on the Ricci flow. Please.
Yeah, yeah. Thank you for giving me the opportunity to speak here. So let me just move on 1 second. Chat. So yeah, so this is going to be a class on recent work that I've conducted with Bruce Kleiner from NYU on uniqueness of weak solutions to the Ricci flow and some topological applications that arose from this. So let me see if this works. So here's a brief outline on how I intend to structure this course. So today, I want to give you some of the preliminaries and some of the background on Ricci flow that are necessary for the class. I'll show a lot of pictures and try to make the definitions as precise as are necessary. Then, and in particular, I want to focus on the blow-up analysis of singularities, so we have a very good idea of what that is, because this will be needed later. And I'll also try to make this main statements or the main results as precise as possible. And so this will require some of the more technical discussion in this part. So this is what I'm hoping to achieve in this first class. Then in the second class, tomorrow, I'll talk about somehow the analytical aspects of our theory, somehow this uniqueness theorem, and in particular the proof of this. And this will also be, I'll also focus on this in the third class. So in the second class, I'll talk more about local stability analysis, which is one important ingredient. And then the third class, how to compare singular Ricci flows, and then I'll finish the proof of this uniqueness theorem. And then approximately in the fourth class, I'll focus more on the topological aspects or applications. So I'll talk more about continuous families of singular Ricci flows, and I'll prove some of the topological applications, and I'll have to just see how time works out and how much I can go into detail. Yeah. All right. So let me see. Okay, wait, one second. I just noticed that. Yeah, 1 second. I may have to change my slides. Okay. So I just noticed I didn't compile the slides on this one, but I can still talk. That's. We remove the handout option. Okay, so the other thing that I wanted to say is I have a handout of these slides that you can download, and I'll just give you the Dropbox link. Where is the Dropbox link? So the Dropbox link is here in the chat. So so you can go backwards on the slides if you need to. Okay, then okay. So just before I start the lecture, let me just say what the main results are that I want to discuss. So this is just a very brief outline, just to give you an idea of what the class will be about. So as I said, there will be this main analytic result that says more or less that given any closed Riemannian manifold, there's some kind of unique or canonical weak Ricci flow through singularities starting from this Riemannian manifold, and that there's some continuous dependence on the initial metric. And again, I'll make this much more precise, but there's somehow this continuity result will be somehow the main analytical result. And this will have topological applications. So for example, it will enable us to show that the space of positive scalar curvature metrics on any closed Riemann manifold is either empty or contractible, or it will make statements on the diffeomorphism groups of spherical space forms. and so on. And again, this is all based on joint work with Bruce Kleiner. All right, so let me now move on to lecture 1, and maybe at this point, let me just switch to my other slide deck. Again, sorry for the inconvenience. I forgot to recompile this after. I'll be there soon, I'm sorry. Okay. Okay. Okay, so this, let me start with lecture 1. And so I'll structure it slightly differently than maybe promised. So I'll first want to make state the main topological results, so the ones that I'm going to prove in the very last lecture. And I'm going to state them first just because they're the easiest results to state, and they will serve as a motivation guiding us through the first lecture, okay? And then in part B, I'll start with the analytic part of this lecture. So I'll talk more about Ricci flow. I'll give a brief motivation on why we should look at Ricci flow, like what this may have to do with the main topological results. And then I'll focus somehow discussing singularities of Ricci flows and Ricci flows with surgery, give you some of the background on Perelman's work. And then in the last part, I'll focus on singular Ricci flows. So these are some improvements of Ricci flows with surgery, and I'll be able to state the main results. Okay, so let me start with the first part, the topological results. Okay, so here are some basic definitions that I'll use in this class. So first of all, M will be mostly a three-dimensional, compact, and orientable manifold, and it should be smooth. And so what I just want to recall is that the topology of three manifolds by now is sufficiently well understood due to the resolution of the Poincaré and Geometrization Conjectures. And this was done in part by Perelman using Ricci flow. So if we just take a three manifold, we basically understand its properties relatively well. So if we want to continue doing topology of three manifolds, we'll have to study objects that are built upon given three manifolds. And so the main objects that I want to study in this class are the following. So first of all, I want to study the space of all Riemannian metrics on a smooth three manifold. And I'll denote this by met M. So this is really just the space of all possible Riemannian metrics on M. Then I'll also be interested in the subset of all those metrics that have positive scalar curvature. So that's, again, still a very big subset potentially. And I'll also be interested in the diffeomorphism group of M. So that's just the space of all diffeomorphisms from M to M. Okay? So all these spaces are very big, and I'll equip those with the C-infinity topology. So what's the C-infinity topology? Well, there is a topology that I can choose on these spaces such that convergence within this topology is equivalent to convergence in every CK norm. Okay, and so now the goal will be to classify these spaces up to homotopy and hopefully using Ricci flow. So maybe I should already get one point, because the space of metrics, I should notice, is contractible. And so that's not hard to see. Well, the space of metrics is just a convex subset in the space, in some other space of all symmetric 0-2 tensors, which is just a vector space. Okay? So if you have a convex subset in a vector space, that's a contractible subset. Okay? So what I want to do now is I want to focus on these two other sets, other spaces of metrics or diffeomorphisms. Okay, I also just noticed I gave you the wrong Dropbox link. Maybe this is the better one here. This contains the handout version. Okay, so let me focus on the space of a metrics with positive scalar curvature. So here's the first main result. This is so the first main result states that the set of all metrics with positive scalar curvature on any three manifold is either contractible or empty. Okay? So either M admits a metric of positive scalar curvature, such as the three sphere or a spherical space form, and in this case, the space is contractible, so it's trivial, or M does not admit a metric of positive scalar curvature, and then the space is empty. Okay? So this is the best possible result that you could expect. And so let me just say a few words on the history of this problem. So first of all, this is true in dimension 2, and I'll actually show you a proof of this using Ricci flow in a moment. This will somehow get us started with Ricci flow. And somehow, well, in higher dimensions, problems of this sort were first considered by Hitchin in a paper of 1974, and then there was a lot of other work, and this work always revolved on showing that in higher dimensions, this space has non-trivial topology. Yeah? So I think the lowest dimension that they obtained was dimension 5. Okay? So it's somehow interesting to see that in dimension 3 there's no the same phenomenon does not occur. And there was also previous work by Marques in 2011 who showed that the space, or if you mod out by diffeomorphisms, is mostly path connected. Okay, so this is somehow an improvement of this result. All right, so this is concerning the space of positive scalar curvature metrics. So let me now move on to the diffeomorphism groups. And here the result is a little harder to state. So let me just start with the diffeomorphism group of the two-sphere. So it was proven by Smale a while ago that if we look at the space of diffeomorphisms of the two-sphere, then this is homotopy equivalent to the space of rotations in R3, so the space of isometries of this two-sphere. And so this was a very nice result. And Smale conjectured that the same should be true if we increase the dimensions by 1. Yeah, and so this was eventually proved by Hatcher using topological methods. And so in dimension 3, there are just now much more, there are many more interesting manifolds, and one class of manifolds would be spherical space forms. Okay? So RP3 or length spaces and things like that. And in order to classify their diffeomorphism groups, what we could do is we could look at the isometry group of this manifold equipped with the round metric, and we could just look at the injection where we take any isometry and view it as a diffeomorphism of M. And essentially, these two results here say that this map is a homotopy equivalence. And so now the generalized Smale conjecture would just say that this map is a homotopy equivalence for any spherical space form. And so this result was verified for a handful of other spherical space forms, but it was open for RP3. And all proofs so far, except for the Ricci flow proofs, they were topological and I would say technical. So and there was no uniform treatment. So basically the idea of proving such a result was to take a spherical space form, and depending on what spherical space form it was, you would have to cut that spherical space form into certain pieces. You could use some embedded surfaces, and then essentially in the end you had some topological balls, and then you could somehow view these balls as some kind of turn them back into spheres and apply Smale's conjecture. So there was some kind of different method that you could use for different spherical space forms. But anyway, so there was no uniform treatment, and it wasn't true for any, and it wasn't done for every spherical space form. Okay? And so recently this was verified for all spherical space forms by Bruce Kleiner and myself. So we showed that the generalized Smale conjecture is true for any spherical space form. And this proof was done by a Ricci flow, and it was somehow the first purely topological application of Ricci flow since Perelman's work. And it also treats all cases uniformly. In fact, we don't even need to know what the possible spherical space forms are. It just works for any spherical space form. And it also gives an alternative proof in the S3 case. It's an alternative to Hatcher's proof. And then I should mention, and we'll get back to this in the fourth class, that there are two proofs of this using Ricci flow. So there's some kind of short proof, which is a relatively short argument, and I hope I can present this in the fourth class, which shows the generalized Smale conjecture, but not in the case S3 or RP3. Okay? It also shows that if M is hyperbolic even, but we have to also assume the Smale conjecture for S3. So if we assume Hatch's resolution of the Smale conjecture, which is true, and we limit ourselves to manifolds which are not S3 or RP3, then we can show this with relatively little work using the analytical tools that I want to present in this class. And then there's also a long proof that where the entire conjecture is proven, and I'll hope to give you some indications on how this is going to work. All right, so just before concluding this, I also want to mention that somehow this Ricci flow technique does not only allow us to show, to classify diffeomorphism groups of spherical space forms, it also allows us to look at diffeomorphism groups of many other three manifolds. So and some of the only caveat here is that for many other three manifolds, diffeomorphism groups have already been classified using some other topological techniques, but somehow we can reprove these things. So for example, if we take a closed and hyperbolic manifold, then we have the same statement, some of this homotopy equivalence, and this was proven by Gabay using topological methods. If M is spherical and geometric, so if it has a homogeneous geometry, then we have the same statement, and this has been proven in all cases but the non-Haken infranil case. And then if the manifold is covered by S2 cross R, by a cylinder, we again obtain similar results, but these were proven by Hatcher, again, using topological methods. But anyway, we get this very uniform treatment using just a single technique. All right, so these are essentially the topological results that I want to get at. And lastly, let me just mention an important equivalence that we need to exploit. So if we want to study spaces of metrics, then it may be kind of natural to use Ricci flows, because Ricci flow will turn out to be some kind of deformation of metrics. But what about diffeomorphisms? How do diffeomorphisms relate with spaces of metrics? And so this is where this lemma, which is relatively well known, comes in. And let me just present this here. Okay, so I'm going to look at a manifold, let's say a spherical space form or even a hyperbolic manifold, and let me fix a reference metric G of constant curvature. Okay, so this should be the space of all metrics on M that have constant curvature, either plus or minus 1. Okay? So for example, if M is a 3-sphere, then this is the space of all metrics that are isometric to the round sphere, but we're not modding out by diffeomorphism. So this is a huge space still. Okay? Then the following is true. Somehow the statement that we want to show in this generalized Smale conjecture, this homotopy equivalence, is actually equivalent to a statement on the topology of the space of constant curvature metrics, namely that the space is contractible. Okay? So in other words, it suffices to prove this in order to prove what we want to achieve. Okay? And so the proof is relatively simple. So let me just highlight this here. So what we need to do is we'll look at a map from the space of diffeomorphisms of M, and we'll map this to the space of constant curvature metrics. And we just do this by taking a diffeomorphism phi and mapping it to the pullback of the reference metric via this diffeomorphism phi. Yeah. So this gives us a map from the diffeomorphisms to the space of constant curvature metrics. This turns out to be a fiber bundle. And while the fiber consists of all diffeomorphisms that leave this metric G invariant, i.e. the isometries. And now we can apply the long exact homotopic sequence. And let's say we want to prove the reverse direction here. So then in this case, if this space is contractible, all these homotopy groups are 0, and therefore the other these maps in between have to be isomorphisms. Okay. So now if these maps are all isomorphisms, then by Whitehead's theorem, this map has to be a homotopy equivalence. Okay. So this is how this works. And the reverse works almost the same way. All right, so this lemma now reduces both of the previous results that I had marked in red to a single result, namely that either the space of both of the spaces of positive scalar curvature metrics as the spaces of constant curvature metrics that they're each either contractible or empty. Okay? So this is essentially the theorem that I want to show on the topological side. Okay? And I want to achieve this via Ricci flow. Okay, let me see if there are any questions so far before I move to the next chapter. Okay. So let me now start with the discussing the more the analytical aspects. So in this chapter, I'll discuss Ricci flow. I'll give a brief motivation, somehow relate this back to the topological problems, and then focus on singularity analysis and also discuss Ricci flows with surgery. So, okay, so let me introduce Ricci flow. So a Ricci flow is a smooth family of Riemannian metrics on a fixed Riemann-manifold, or in a fixed manifold of any dimension M. And the Ricci flow equation is that the time derivative of the metric is equal to -2 times its Ricci curvature. And then we have some initial condition very often. And so the reason why we care about this equation, very broadly speaking, is because if we write this equation up in harmonic coordinates, using some of the, when you look at the metric coefficients, then this looks approximately like a heat equation, okay? Like some nonlinear heat equation. I'm lying a little bit here, but the idea is that we hope that that this flow will improve the metric as we move forward. Somehow we'll make it more homogeneous. And so the Ricci flow equation was introduced by Hamilton in 1982, and in the same paper, Hamilton also showed that the flow has a unique solution for some maximal time. Okay? So if we start with some initial condition, we have some unique solution, let's say on a compact manifold. And the solution either exists for all non-negative times, in which case we call the solution immortal, or it somehow ceases to exist at some positive time. And in this case, we say the solution develops a singularity at time t. And this can be detected by the fact that the curvature, the norm of the Riemannian curvature, blows up as we reach that time. All right, so here is a very, somehow the most basic example that you can think of. So this is the example where we start with a metric that is Einstein. Okay? So Ricci is equal to some multiple of the metric. And in this case, the Ricci flow equation will just imply that the metric evolves via rescaling. So this is some of the only one of the few classes of examples where we can write down a solution to the Ricci flow explicitly. Okay? So here are somehow the most important pictures that we should keep in mind. So for example, if we take a round sphere, and this has positive Einstein constant, then this round sphere will shrink under the Ricci flow. And this coefficient will be 0 if we choose, will be 0 at some point. And so that means that the diameter of the manifold shrinks to 0 at some finite time. And where it shrinks to 0, that's where the singularity occurs, okay? Because the curvature there blows up and goes to infinity as we shrink down the manifold. If lambda is 0, then one example would be a flat torus, which would just be constant under the Ricci flow. And for lambda being negative, one other example would be a hyperbolic manifold, which just expands under the flow. All right. So these are some of the most basic cases, but most often we are more interested in Ricci flows. That's where we start at some maybe very complicated geometry, and we hope that the Ricci flow simplifies these geometries and takes them to some nicer, maybe Einstein geometry and so on. And so let me just discuss what happens in dimension 2. So this is the two-dimensional case, which is very well understood. So in dimension 2, this is in fact completely true. So what if we take any let's say compact two-dimensional manifold, and we put any metric on this two-dimensional manifold, no matter how complicated it is, the Ricci flow will always simplify this metric and will somehow converge modular rescaling to some of these to some constant curvature metric. Okay? So this is a very remarkable result. So in particular, what I just want to highlight here is that if we're on S2, then we can then the flow will develop a singularity at some time, which we can actually compute based on the volume or area of the initial data. And then the metric near the singularity will be asymptotic to some factor times the round metric. So if we rescale just by the opposite of what we've seen on the previous slide, then the metric converges to a round metric. And so this result, can really be used to reprove the uniformization theorem. Okay, so this way we can prove that for any, maybe phrased in different words, we can use this to prove that any compact surface admits a constant curvature metric, or maybe a slight generalization of this result. So it can somehow, the result can be used to produce constant curvature metrics. But we can also interpret this result slightly differently. We can view this result in somehow space of metrics. So let me do this here. So what I tried to draw here is, so this big circle should indicate the space of all metrics on the two-sphere or on any manifold. And then this medium circle should indicate the subset of all positive scalar curvature metrics. And then the smaller circle indicates the set of all constant curvature metrics on M, or positive constant curvature metrics on M. And what we could do is, if we take this picture, we can view Ricci flow as some kind of dynamical system on this space of metrics. Okay, so Ricci flow is essentially some vector field, and its trajectories are solutions to the Ricci flow. Okay? So this is here some kind of trajectory. Okay? And so what Hamilton and Chow's result basically states is that any of these trajectories, that they will limit to the space of constant curvature metrics eventually. Okay, so this is another way of stating the Hamilton-Chow result. So there's some kind of deformation retraction onto this constant curvature metric, the space of constant curvature metrics. Then the other thing that I should mention is that if we have a metric of positive scalar curvature metric, then the Ricci flow will preserve the condition of having positive scalar curvature. Okay, in other words, if we start somewhere within this space, within this intermediate space, then the Ricci flow will remain within this intermediate space. Right? And so what this implies is that this Ricci flow gives us, modulo some work, and this is just a more conceptual picture here, is that the Ricci flow gives us a deformation retraction from either the space of all metrics or from the space of positive scalar curvature metrics onto the space of constant curvature metrics. Okay, so maybe we have to do some rescaling here, and we have to take some limit, but essentially the Ricci flow will allow us to deformation retract this big space or the intermediate space onto this small space. Okay? And so this has a topological consequence, namely that all these spaces of metrics have that they're homotopy equivalent to one another. And as I mentioned before, the space of all metrics is contractible. So therefore, all these spaces are contractible. And then by the lemma that I showed you a few slides ago, this implies the Smale conjecture for S2, okay? Or Smale's result for S2. Okay? So this is some of the most somehow toy application of Ricci flow. And basically what I want to do in the course of these classes is I want to generalize this idea to dimension 3. Okay, sorry, maybe are there any questions so far? Okay, so now we want to replicate this idea in dimension 3, and we'll see that in dimension 3 we'll have, we'll be confronted with a lot of difficulties. So first of all, the picture that it's just not true anymore that the Ricci flow will always converge to some nice metric. So the flow may incur some non-round or non-global singularities. So we'll have to deal with this. There will be some necessity to extend the flow past the first singular time. So you may have heard of surgery, so we'll have to discuss those. And then we'll have to worry about continuous dependence on the initial data. So let me maybe highlight this on the previous slide. So the whole proof of this theorem is only works if we somehow have some kind of continuity of this deformation retraction. Right? So deformation contraction has to be continuous. And so this would be associated to continuous dependence of these trajectories on the initial condition. Okay, So essentially, we need to somehow the proof relies on the fact that if we deform the initial data of a Ricci flow, then the Ricci flow depends continuously on that. And so that's not difficult to prove in the two-dimensional case. But in higher dimensions, or in dimension 3, if we incur singularities, then we have to somehow do certain surgery procedures, then this may create a big obstacle. Right, so we have to discuss this as well. And so in order to carry out the same idea in dimension 3, we will need an analytical result. And let me just foreshadow and tell you where we are going to go in the first 3 classes. So essentially, I want to show you that this result of Kleiner and myself, where we show that if we take a 3-dimensional manifold, there's some kind of unique or canonical weak Ricci flow that may incur singularities, but that somehow flows through these singularities in a canonical sense, and that we have continuous dependence of this flow depending on its initial data. And I'll make these things a bit more concrete, but this is why we need this uniqueness and continuity result here. Anyway, so let me now focus on Ricci flows in dimension 3, and let me just approach this result a bit more slowly. Okay? So what I first need to discuss is somehow the possible singularities that we may incur, that the flow may incur in dimension 3. And so in order to discuss this, I will have to present this famous example of the rotationally symmetric dumbbell. Okay, so this is an example that will show us what kind of singularities we can expect in 3-dimensional Ricci flow. Okay, so here's what the example shows approximately. So what I'm looking at here is a rotationally symmetric metric on the 3-sphere. So it's not the round metric on the 3-sphere, it's just rotationally symmetric by an O3 family of rotations. Okay? So I can write this metric as a warp product of S2s over an interval. And so essentially I can describe these metrics by the warping function. And so now, okay, so maybe I should say what this warping function looks like. So it looks like in such a way that the manifold is isometric to a piece of a round sphere of radius R1 on one side, and then a piece of a round sphere of radius R3 on another side, and they're connected by a neck that has approximately width R2. Okay? So for any radii R1, R2, and R3, I can somehow write down some warping function of this form. So the precise form won't be important for us now. And so now if I evolve this metric by the Ricci flow, the rotational symmetry is being preserved, and we can study some of the evolution of this flow by looking at how the warping function evolves. Okay, so what people have found out is that in this example, the Ricci flow will always incur a singularity in finite time. But some of the main difference to dimension 2 is that the type of singularity that we see depends on how we choose the radii R1, R2, and R3. So for example, if we choose the radii comparable to one another, then somehow this neck is relatively thick, and this negative curvature coming from the concavity of the warping function will cause the neck to widen up until it somehow dissolves, and the manifold will become more and more round and shrink at the same time, and then develop a singularity here. Okay? So if we want to know what the singularity looks like, what we can do is we can rescale, we can magnify the singularity, and we'll see that the singularity is asymptotic modular rescaling to a round shrinking sphere. Okay? So this is in some way the singularity model here. Okay? We call this case the extinction case because the manifold looks like it disappears. Okay? On the other hand, if we choose the neck much thinner, so the neck is much more pronounced, then we have a lot of positive curvature here on the neck, which comes from the cross-sectional 2-sphere. And that's somewhat different from the 2-dimensional case. Remember, in the 2-dimensional case, the cross-sections would just be circles, so they wouldn't have positive curvature. However, in higher dimensions, they have positive curvature. So if we just choose the neck very, very thin, then there's much more positive curvature here in the neck than there's negative curvature coming from the concavity here. And this will cause the neck to contract and then limit in some kind of neck pinch singularity. Okay? So the neck will have thickness 0 asymptotically. And again, if we want to understand the singularity here, we can rescale, and what we'll see is something that's asymptotic to a round shrinking cylinder. So the cylinder looks like S2 cross R, where the S2 factor contracts to a point while the R factor remains constant. Interestingly, this metric is only local. So the singularity is only local. So the singularity only occurs here, and the metric here actually limits to some smooth metric at the singular time. And then there is an intermediate case. So this is called the neck singularity case, or neck pinch. And now there is an intermediate case where two of these things happen at approximately the same rate. And what we see in this case is we see some kind of singularity at the tip. Okay? So there, the curvature somehow goes to infinity here. And now if we magnify and look what this singularity looks then what we'll see is some kind of paraboloidally shaped singularity. This is also called the Bryan soliton. It looks like this. So the singularity kind of corresponds to this, this tip here. And this is often called a cap singularity. So already, if we just look at this very basic rotationally symmetric case, we see these three different types of singularities or singularity models that can occur. So we can now ask, well, what happens if we start with a non-rotationally symmetric metric? What happens in dimension 3 if you just start with any Riemannian metric and we run into some singularity? What does the singularity look like? And so this is essentially, in a very imprecise form, or really in a very rough form, where Perelman's big discovery comes in. So Perelman could show that the singularities that we've observed in the rotationally symmetric case on the previous slide, in some way are essentially all the three-dimensional singularities that we see in the general case. So what I've shown you in the previous slide really entails all the different behaviors that we see in the general case. So this was a very good example. And so what I want to do in the next few slides is I want to somehow make this statement more precise. Right? I want to really tell you what this means, this statement. And so in order to do this, we'll have to discuss a few topics. So first of all, we'll have to discuss the no local collapsing theorem, which is somehow maybe one of the groundbreaking results by Perelman, on which maybe most of these results are based. Then we'll have to discuss geometric convergence of Ricci flows. So we'll have to discuss blow-up analysis of singularities, which leads somehow to the study of singularity models. And we'll have to discuss a qualitative classification of singularity models. Okay? So this will make more sense in the next few slides. Okay. Are there any questions so far? Sorry. Okay, so okay, so let me now move to the no local collapsing theorem. And so this is really a result that holds in any dimension. Okay, normally I only care about 3 manifolds in this talk, but this is a result. This is true in any dimension. So what do we want to achieve? So some of the main thing that people were concerned with before Perelman's work was somehow that they wanted to rule out that there are singularities in Ricci flow that look like some small S1 factor cross some n-1 dimensional surface. Okay? So some of the, what we've seen in the previous few slides is that there are singularities where a 3-sphere contracts or where a 2-sphere contracts. Okay? But some of the worry was that there may be singularity where an S1, like a circle contracts over some surface which may not contract. Okay? And so this is something that we want to rule out. And the idea how this was ruled out was using this no local collapsing theorem. Okay? And so this theorem states the following. It says that there is a constant kappa, which only depends on the dimension, on the final time of existence, and on the initial metrics, only in some certain soft geometric quantities on the initial metric, like some volume or diameter bounds, such that the Ricci flow is what Perelman called kappa non-collapsed at scales less than 1. Okay? So I should tell you what kappa non-collapsed means, or kappa non-collapsed at scales less than 1. So this means that whenever you take a point on X and a time in the time interval, and I choose a scale between 0 and 1, so below 1, then the following is true. If I look at the ball around x with the time, equipped with the time t metric of radius r, so essentially I just take the ball of radius r around x with respect to the time t metric, and if on that ball I have an upper curvature bound of this form, so this is r to the -2. So in other words, if I scale the ball of radius r to have radius 1, then I would have an upper curvature bound of 1 on this ball. Okay? So if I have this curvature bound on this ball, then I have a lower volume bound on the ball, kappa times r to the n. Okay, again, if I rescaled the ball to have radius 1, this would just say if I have a curvature bound, upper and lower curvature bound of 1 on the ball, then I have a lower volume bound of kappa of this ball with respect to the time t metric. Okay? And so this really now helps us to rule out these singularities, because if we had an S1 fiber, an S1 factor that would contract, that would become smaller and smaller, then this would not increase the curvature but decrease the volume. So if epsilon was very small, then for maybe some small enough r, we would still have this condition. But assuming epsilon is very small, this condition would be violated. So this theorem allows us to rule out these types of singularity models. Okay? And maybe a slightly more useful consequence even of this no local collapsing theorem would be where we can replace the lower volume bound by an injectivity radius bound. Okay? So if we have a two-sided sectional curvature bound and a lower volume bound, then by Gromov's theorem, this implies a lower bound on the injectivity radius. Okay, so we have this result, which will be somehow is more or less fundamental in most of Perelman's results. Are there any questions on this? Okay, so then the next ingredient that I need to discuss is a blow-up analysis. Okay? And so a blow-up analysis are quite common if we just study geometric equations, and this is just similar to many other blow-up and just blow-up or limit analyses. So let me review blow-up analysis in somehow the setting of Ricci flows. So what I try to draw here is I try to draw the space-time of a Ricci flow. So the x-axis should indicate the manifold, and the y-axis should indicate time. And so I assume that I have some singularity where this dashed line is. Okay? And so if I have a singularity, then I should be able to choose a sequence of points and times, xi and ti, that I would say run into the singularity. So what do I mean by points running into a singularity? Well, I mean that if I take the curvature at these points, then the curvature goes to infinity. Right? So we know a singularity occurs where the curvature blows up. I just want to take a sequence of points whose curvature goes to infinity. Right? So I can always do this if I have a singularity. And then I need something a bit stronger than that. I need an addition. I need to choose these points xi, ti, such that for some sequence ai going to infinity, I have a curvature bound of the form c times qi on a parabolic ball of size ai times qi to the -1/2 around xi, ti. Okay? So what I mean by this, so a parabolic ball is just, this is just a ball of radius r around the point x at time t times the time interval where I go backwards by r squared. Okay? So in a Ricci flow, time scales like r squared. So we can think of time as having the unit square meters, while distances have the unit meters. So that's why I have to subtract minus r squared. So here I've tried to draw this here. So this rectangle here would be a parabolic neighborhood. So I take the ball around xi, ti of this radius, and then I go backwards in time by the square of this radius. Okay? So this is a parabolic neighborhood, and I draw this around every point. So what does this condition mean, essentially? Well, if I were to rescale my Ricci flow parabolically, so in time and in space and in time, by by qi, by the square root of qi, then distances would multiply by the square root of qi. So the parabolic ball would have radius ai going to infinity. And the curvature would divide by qi. So the curvature at the base point would be 1. And this curvature bound would mean that we have a uniform curvature bound on this parabolic neighborhood, which is independent of I. So this is what this extra condition would mean. So the extra condition means that if we rescale to normalize the curvature at these base points, then on larger and larger parabolic neighborhoods, we have a uniform curvature bound. Okay? So there's some generalizations of this condition, but this is essentially good enough for our purposes for now. Okay? So this is an extra condition that I have to put on the choice of these points xi and ti. But just to think about this briefly, so this can always be achieved. So if I have some singularity, what I could do, for example, is I could look at, for every time I could look at the maximum of the norm of the curvature at that time t. And then I could choose times such that at times ti, such that at time ti, I'm attaining the maximum of the curvature compared to all previous times. And I could just choose xi to be the maximum in that, where the maximum is attained in that time slice. Okay? Then we have this curvature bound not only on these parabolic balls, but on all previous times. Okay, so I can always choose xi, ti so that this is satisfied. Okay, so now once I have this sequence of points, what I can do next is I can parabolically rescale the Ricci flow. Okay? So I can multiply the metric by qi, and then I'm parametrizing the time in this way. So this is essentially will rescale distances by the square root of qi and times by qi, and it will divide curvatures by qi, and I'm applying this time shift, which will mean that time 0 for this flow corresponds to time ti for this flow. Okay, so essentially for the new flow, these points would be situated at time 0. Okay? And so these new flows are now defined on this time interval. Okay, so from minus qi ti up to time 0, and the time 0 would correspond to the time ti. And note that since qi goes to infinity, this product goes to infinity. So these flows are defined on longer backwards time intervals. And well, now this curvature bound means that after rescaling, I just have an upper curvature bound on larger and larger backwards parabolic neighborhoods. And then what I can do next is I can apply the no local collapsing theorem. Well, I have an upper curvature bound, so the no local collapsing theorem implies a lower injectivity radius bound at the base point. Yeah? So I have an upper curvature bound on larger and larger parabolic balls, and I have a lower injectivity radius bound. And so these conditions allow me to apply geometric convergence. So after passing to a subsequence, I get geometric convergence of these pointed Riemannian manifolds. Okay, so this is GI at time 0. Okay, so I have an upper curvature bound, uniform upper curvature bounds here, and a lower injectivity radius bound. So I can apply Cheeger-Gromov convergence, and this will imply that these Riemannian manifolds will converge to some limiting Riemannian manifold, which I'll denote by M bar, G bar, X bar. Okay. So maybe I should say, so Cheeger-Gromov convergence is a stronger version of Gromov-Hausdorff convergence, and in order to get C-infinity convergence, we also need curvature bounds on the curvature derivatives, but they can be obtained from curvature bounds via derivative estimates on the metric. So these metrics are, since these are metrics are time slices of Ricci flows, we also have curvature derivative bounds. All right, so now I know that essentially if I take these pointed time slices, I rescale them such that the curvature at the base point is 1, then these pointed time slices converge to some limiting metric, M bar, G bar. So just to recall, what does this mean? What does this convergence statement mean? Well, it means that there exist diffeomorphisms onto their images. Let me denote them by psi I. From some sequence of larger and larger balls around the origin in this limiting manifold, AI prime goes to infinity, to mi, that carry the base point x bar to the points xi, such that AI prime goes to infinity, and such that if we look at the pullbacks of the metrics gi0 via these diffeomorphisms, we converge to g bar and the local C infinity sense. Right? So g bar so this guy here converges uniformly, locally uniformly, and all its derivatives converge locally uniformly. Okay? So this is the meaning of Cheeger-Gromov convergence. So this generalizes Gromov-Hausdorff convergence, for example, or strengthens Gromov-Hausdorff convergence. Okay. Are there any questions on this slide? Okay, so let me move on and now bring in some of the Ricci flow aspect of this. So this is just a convergence of Riemannian manifolds. So what I could do next is I could look at the corresponding Ricci flows on these manifolds. This is just the final time slice of a Ricci flow. And recall that we have upper curvature bounds on backwards, larger and larger backwards parabolic balls of these Ricci flows. So using these curvature bounds, we can now deduce bounds on derivatives, on arbitrary derivatives of these pullbacks here. Okay. So this is a little bit of technical work, but this can be done. So these metrics, if we look at the pullbacks of these flows, then these become Ricci flows and M bar, and they start from some metric that's very close to G bar, and they evolve by the Ricci flow with bounded curvature, so we will be able to get some derivative bounds. And so these are, we have these derivative bounds, and now we can use some Arcelor-Ascoli, and we obtain that after passing to a subsequence, not only the time zero metrics converge to some G bar, but all the metrics converge to G bar T. Okay, so in the local C infinity sense, so all the time derivatives and space derivatives and so on. So if we pull back by these same diffeomorphisms and recall they are fixed, they don't depend on time, then these converge locally or uniformly to some Ricci flow G bar. And while this Ricci flow is then defined, remember these flows are defined on larger and larger compact time intervals, this limiting Ricci flow is now defined on for all non-positive times. So it's an ancient Ricci flow whose final time slice is equal to G bar. Okay, so let's just recap what did we do? Well, we've taken this we've taken a single Ricci flow. We turned it into a sequence of Ricci flows defined on backwards time intervals by some parabolic rescaling, and we've taken these Ricci flows to a limit. And so this kind of limiting process is called Hamilton, it was developed by Hamilton. So I'll denote this by Hamilton Cheeger-Gromov convergence. Okay? C infinity Hamilton Cheeger-Gromov convergence. Right? So we can basically say that the sequence of these rescaled flows converges to an ancient flow in this C infinity Hamilton Cheeger-Gromov convergence. And what we mean by this is really just that there is a sequence of these diffeomorphisms psi I on larger and larger balls, such that we have smooth convergence of all the Ricci flows if we pull them back. Okay. Right. So now we have convergence of these flows to some limiting flow. And well, what does this mean? Well, this means that somehow if we knew what this flow was, then we would have some local models of the original flow near xi. So let me just go backwards on the slide one more time. So these points xi and ti, they converge, they run into some singularity. And we now know that after rescaling, the geometry of these parabolic neighborhoods, pi, becomes closer and closer to m bar, g bar. Okay? So then this means that the local geometry near these points is very close to the limiting geometry. So this will tell us what the local geometry near these points is essentially. All right, so let's just compare this with the picture from before. Let's consider, for example, this next singularity. So if we wanted to understand this next singularity on a more mathematical level, then what we would do is we would take a sequence of points xi and ti that would get closer and closer to this neck. So they would sit somewhere in the middle of these necks that become thinner and thinner. And then we would have to parabolically rescale these flows. So these flows will be defined on very long time intervals. And the geometries are near these points will look very, very close to a cylinder. And eventually these flows will converge just to this cylindrical flow, this green flow. Okay? So some of these green Ricci flows that I drew before are just blow-up limits of the original flow. Right? So they're essentially the singularity models or blow-up singularity models of the original Ricci flow if we just choose xi, ti appropriately. All right, so maybe with this new terminology, I can now state Perelman's main result on some other classification of singularity formation in a more precise way. Okay? So instead of saying essentially these are all types of singularities, we can now say all blow-up models of any Ricci flow that develops a singularity at time t are something, and the something is called a kappa solution. Okay? So I need to tell you what a kappa solution is. Right? So this basically classifies in a certain way what singularities look like, what the formation of singularities look like, by saying what the singularity models are. Okay? So what's a kappa solution? Well, a kappa solution, so the precise definition won't be so important for us, but let me just write it down here once. A kappa solution is an ancient Ricci flow, as it defined for all non-positive times, that satisfies certain conditions. So it has non-negative sectional curvature, it has positive scalar curvature, it has bounded curvature in general, and it's kappa non-collapsed at all scales, which just means that the same statement is true, but we don't require R to be less than 1, which R should just be positive. Okay, so essentially what we're doing in the slide is we're cheating a bit. So maybe what I should say is these properties here, they're chosen because we know that when we take a blow-up limit of a Ricci flow, that these properties are all given. Somehow it's somehow possible to show that any blow-up limit has to have non-negative sectional curvature. It's possible to show that it has to be kappa non-collapsed, and so on, and so on. So the kappa non-collapsedness passes to the limit, and so on. Okay? So essentially what we're saying in this statement is a little bit of cheating. We're saying all blow-up models are flows that have the properties that we know blow-up models to have. Okay, so this statement in itself is maybe not very strong. However, it turns out that given these conditions of a kappa solution, we'll be able to classify what kappa solutions look like. Okay? And somehow this statement is only strong with the what I'm going to show you in the next slide, namely the classification of kappa solutions. Right? So this was done by Perelman. He took all these properties of kappa solutions, and then he could classify them and show that they belong to three different, there are basically three different categories of kappa solutions. So there's one type of kappa solutions that belongs to somehow the extinction case. In this case, the manifold is compact. So it's a quotient of a 3-sphere. And the manifold, if gamma is 1 or Z2, so if this spherical space form here is non-trivial, let's say it has complicated topology, meaning that gamma should not be 1 or Z2, so M bar should not be S3 or RP3, then the flow is just round. It's just a quotient of the round sphere that shrinks down to a point, just as what we've seen in the rotationally symmetric case. There's another type of solution which could also look somehow kind of like an ellipsoid, and this could occur if gamma is equal to 1 or Z2. So it's an ellipsoid or it's a Z2 quotient of that. So that would be another possible kappa solution. The other possible classes of kappa solution would be the ones that correspond to necks. So in this case, M bar is just S2 cross R, equipped with the shrinking metric. Right? So it's just the metric where the S2 factor shrinks to a point, and the R factor remains constant, modular rescaling. And gamma could either be 1 or Z2. So either we have the cylinder or its Z2 quotient. So where we just look at the antipodal map on S2 and the reflection on R. And then the other case would be some kappa, like some paraboloidally shaped kappa solution. And in this case, M bar is just R3. And we know that there's some kind of compact subset such that away from this compact subset, the manifold looks approximately like S2 cross some interval. Okay? And more or less, it becomes more and more rotationally symmetric as we go out to infinity. And you could somehow say it's somehow cylindrical near infinity. Okay? So it's not asymptotic to a fixed cylinder, but somehow it opens up, and locally it looks more and more cylindrical. Okay? So this is what is called the qualitative classification of kappa solutions. So, and now, if we put together the previous theorem saying that the blow-up model of every singularity in 3D Ricci flow is a kappa solution, combined with the classification of kappa solution, we somehow reproduce some of this idea that I've shown you in the rotationally symmetric case. So these three different families of kappa solutions, they really are analogous to the three different behaviors in the rotationally symmetric case. And so this really states that what we've seen in the rotationally symmetric case is more or less what we see in the general case. All right, so let me focus a bit on this intermediate case here, the cap case. So this is maybe the case where Perelman obtained somehow a more or less incomplete classification. But there was a very prominent example in this case. This is called the Bryan-soliton. And so we'll need the Bryan-soliton later. So the Bryan-soliton is a Ricci flow which exists for all times. Again, it's defined on R3. And it's going to be rotationally symmetric. I'm going to denote by x bri the center of rotation. So this is just the base point. So x bri would be here. So it's really a rotationally symmetric solution. So I can express it using a warping function f, where the fiber of the warp is S2. And the warping function behaves like square root of r at infinity. So in the Bryan-soliton, this paraboloid opens up like square root of r. And it's called a soliton because it's a steady soliton. So what's a steady soliton? A steady soliton is a Riemannian metric where the Ricci curvature is equal to the Hessian of some function f. And sorry, I should have chosen a different f here. This is not the same f as here. Okay? So this is some different f. And well, the Hessian of a function is equal to the Lie derivative of the metric of 1/2 times the gradient of this function. And so this implies that the corresponding Ricci flow corresponding to this metric evolves, remains constant modulo diffeomorphisms. Okay? So this means that essentially, if we deform by the Ricci curvature, then that's nothing. Then that's somehow the same as pulling back by a family of diffeomorphisms. Okay? So essentially, it shows that all time slices of the Bryan-soliton, they're isometric to one another. And some of these families of these isometries, they are essentially given by the flow of the gradient of f. Okay? So this is a very important class of examples, the important flow in this topic. All right. So this is somehow Perelman's qualitative classification of kappa solutions. And for all of his applications, this turned out to be enough. But after Perelman's work, there has been some development and some efforts in classifying these kappa solutions even further. And so maybe the first important work in this direction was conducted by Bamler in 2011. He showed that if we take a kappa solution that's also a steady soliton, it's not hard to see that we have to be in the cap case in this case. Then the kappa solution has to be homothetic to the Bryan-soliton. Okay, so the Bryan-soliton is the only kappa solution that's also a steady soliton. Okay, in the definition, thanks, Gilles. Yeah, so sorry, I should have said that in this definition of a steady soliton, I said a steady soliton is a single Riemannian metric on a manifold, and then we can get every other, then we can evolve this Riemannian metric by pulling back by by a family of diffeomorphisms. But yeah, you're right. If I put some of the Bryan-Soliton metric here, then f would also depend on time. Yeah, and f would just evolve again by pullback of the corresponding diffeomorphisms. Okay, yeah. So again, it was remarked that we can also define a steady soliton equation for a Ricci flow, in which case f would have to depend on time. Yeah, thank you for the remark. Okay, so another interesting result in this direction was obtained by Hamilton, who showed that if we look at a kappa solution, or even any general ancient solution to the Ricci flow, then the time derivative of the scalar curvature at any point is non-negative. So at any point, the scalar curvature has to increase. So this was quite a remarkable result. So this is based on some kind of Harnack inequality, which is and it really relies on the fact that we're looking at an ancient solution. Okay? So the scalar curvature does not have to somehow, really has to increase pointwise. Okay? And what Hamilton did is he also considered, well, what happens if we have equality at one point? Okay? And so then there's some rigidity discussion, which actually allows us to deduce that if we have equality at some point, then this kappa solution has to be a steady soliton. Well, but then if we have a kappa solution, which is a steady soliton, then we have to be homothetic to the Bryan-Soliton. Okay? And again, then this point x has to be the point on the Bryan-Soliton where the scalar curvature is, where the time derivative of the scalar curvature is 0. And that has to be the base point, okay? So in total, what we get is that if on a kappa solution, the time derivative of the scalar curvature is 0, then we immediately know that it's a Bryan-Soliton, and we also know that the point is the center of rotation. Okay? So this is a very strong rigidity result. Okay? Okay? Or in other words, if we had a kappa solution which is not the Bryan-Soliton, or if we were on a Bryan-Soliton and are not on the center of rotation, then dt of r has to be positive, strictly positive. Okay, so this is another result that we'll be relying on later. And then more recently, the classification of kappa solutions was in fact was in fact completed by Brenle, Angenen, Daskalopoulos, Sesam, and there's some alternative approach by Bruce Kleiner and myself. So in fact, what we now know is that every kappa solution is just homothetic to a quotient of either a round sphere, a cylinder, or it's homothetic to the Bryan-Soliton, or it's homothetic to an ellipsoid, or it's Z2 quotient. Okay? And there's a certain type of ellipsoid that one can define. Okay? So just to show you the picture before, what we now know is that in this case, kappa solutions are either round, or they're Perelman's ellipsoid, or the Z2 quotient. In this case, they have to be isometric to the Bryan-Soliton. And well, in this case, we already knew that there are cylinders or quotients thereof. Okay, so now instead of talking about kappa solutions, we could just also give a list of a few different types of Ricci flows. However, so this is a very nice result. However, this was not needed for the uniqueness theorem that I want to present in this series of lectures. So just by, because this result was obtained later. All right, so, okay, so to recap, we know that every singularity is somehow, the blow-up of every singularity is a kappa solution, and we know what kappa solutions look like. So what I want to do, and sorry for beating this dead horse, but I want to put some of these, these results into a slightly different framework, which will help us later to somehow work with these terminologies more efficiently. Okay? Right, so let me just revert what we've done. And I'm going to introduce a new concept here. So let me just take a Riemannian manifold, Mg. I'll try to draw this here. It's M. And I'll take a point on X on M. Okay? So think of this as the time slice of some Ricci flow. And so what I'm going to define now is I'm going to define the curvature scale of rho at this point. So the idea here is that is essentially, don't worry about the 1/3 here for now. I'm going to take the scalar curvature of this point. Let's assume for simplicity that we have positive scalar curvature. I'm going to raise this to the power of -1/2, right? So scalar curvature is measured in 1 square meters. So if I raise this to the power of -1/2, then I get a quantity that's measured in meters. So a scale, a length scale. And the reason, so this is just for convenience. I want to think of, because I'm using curvature to somehow compute a local scale. And instead of talking about curvature, I just want to talk about something that's a distance. That's a length, basically. So this is how I define this curvature scale rho. And the 1/3 will just be for convenience. You'll see later. That's really not important. Then so what I want to do now is I want to understand the geometry near this point X at scale rho. And so I'll do this by fixing some model metric, m bar g bar, with some base point x bar. Again, it's some pointed Riemannian manifold, or I call it model space. And I'm going to say that m bar g bar x bar is a local epsilon model at x if there's a diffeomorphism from a large ball of radius 1/epsilon around x bar onto its image in M, such that the image of x bar is equal to x, and such that if we pull back the metric on M to M bar and rescale by rho to the -2, so we want to normalize rho, somehow the curvature scale to be 1, then the pullback of this metric is close to G bar in some large CK norm. Okay? So this really means that this gray region is geometric close to this gray region. This is just some terminology. Now let me take a Ricci flow, and now I'm going to coin this terminology that I'll be using throughout this class. So I'm going to say that this satisfies the epsilon canonical neighborhood assumption at scales less than R0 if for any point x at any time t whose curvature scale is less than R0, so meaning whose curvature is bigger than r to the -2. Okay? So meaning if I take a point whose curvature is large, then this point at time t is locally epsilon modeled on the final time slice of a pointed kappa solution. Or the pointed kappa solution is a local epsilon model at x. Should have used the same wording here. Okay, so now let me restate Perelman's result one last time. So essentially Perelman's result now states that every three-dimensional Ricci flow satisfies the epsilon canonical neighborhood assumption at some small scales below some scale r, which may depend on epsilon. Right? And so no matter how small I make epsilon, somehow if I look at points whose curvature scale is very small, i.e. where the curvature is very large, Perelman could show that the neighborhood of these points looks close to a kappa solution and therefore is close to a neck, like a cylinder or a Bryan-Soliton and so on. So this is somehow the nicest way of stating Perelman's result. Yeah. And so I'm skipping some of the ideas how this is proven, but yeah, essentially this can be proven using some blow-up analysis. Yeah, so assume this is not true, then we would find smaller and smaller points of smaller and smaller scales that are not close to kappa solutions, but then we can pass to a limit and get a kappa solution. Anyway, so this is all that we need to somehow recall. Okay, so essentially, if we take a Ricci flow and we run up until like very close to the first singular time, then we know that if we look at the points that have high curvature, that somehow a neighborhood of all these points looks like a cylinder, a Bryan-Soliton, or like a sphere. Okay, so we can really understand somehow the set of all points where the curvature is large. And so this discovery allowed Perelman to devise what is called a Ricci flow with surgery. Okay? So this allows us to extend the flow past the first singular time. Okay? So let me now define what is a Ricci flow with surgery. Well, a Ricci flow with surgery is essentially given by a sequence of Ricci flows parameterized by consecutive time intervals that are defined on manifolds of possibly different topology, M1, M2, and M3. And the precise definition of a Ricci flow with surgery is a bit more involved and more technical, and I don't think it will be very useful. So instead, let me just show you a quick movie what we want to do. Okay? So let me start with some initial condition, some three-dimensional Riemannian manifold, compact, closed. Then we can evolve this manifold by the Ricci flow. And let's just stop, maybe let's stop a nanosecond before the first singular time. Then we see all these points where the curvature is very large. And while we know that, now we know by this epsilon canonical neighborhood assumption, we know that the neighborhood of all these points looks either cylindrical, Bryan-Soliton-like, or spherical. Okay? So let's assume that in this case, all the points all have cylindrical neighborhood. So we see this kind of tube here, a very thin tube. And what I'm going to do now is I'm going to locate very small cross-sectional two spheres in this tube. And I'm going to cut the manifold along these two spheres. Okay? Let's say somehow the cross-sectional two spheres have radius delta or scale delta for some small delta. So I'm going to cut along these two spheres. I'm going to throw away the intermediate part, which is just cylindrical. And then I'm going to glue in three disks here of a certain nice geometry. The details won't be important. Okay? So what I'm doing by here is that I'm making the manifold less singular. So I can hope that I can evolve this manifold by the Ricci flow for a longer time. And I'm also changing the topology, but in a very controlled way. Namely, essentially, I can obtain this manifold from this one by performing a connected sum between these two pieces. Now, the next thing I can do is I can run the Ricci flow starting from this manifold again, and then I continue the surgery process. So maybe I see another next singularity. And so here, maybe I see a singularity that's modeled on a round sphere. In this case, I say the component becomes extinct and I just discard it. Okay? And then I run the flow again and so on and so forth. Yeah. Okay, so just to recap, we have these Ricci flow with surgery is given by the sequence of Ricci flows, and there is some kind of relation between these Ricci flows with surgery given by what are called transition maps. Okay, so this, so to be precise, what I'm doing here is for every time ti, I'm going to look at the set of points ui minus in the somehow the pre-surgery time slice, the set of all points that are not affected by surgery. And then I'm also going to look at the set ui plus of all points that in the post-surgery time slice, an M2, that that somehow also are not affected by surgery. And we know that if we look at the metrics after performing a surgery and before performing a surgery, they don't change by the surgery. Okay, so we really have an isometry between this time slice and this time slice modulo this region where the surgery was performed. Okay. Okay. And so these maps, phi, I will call them transition maps. Okay. So they will just tell me if I look at a point here, where is the corresponding point here surviving into the new flow. And then also the surgery process depends on what is called a surgery scale delta. Okay? So in order for this process to work out, we have to choose delta very small. Okay? So if we choose delta small, then Perelman showed that this process can be continued indefinitely. Okay? And the important part here is to show is that we don't have any accumulation of surgery times. Okay? So what we could always do is I could always write down some surgery process that will cut away some bad parts of the manifold. But what would potentially happen is that if I, restart the flow again after the first surgery, then I perform another surgery and then I restart the flow again, that somehow the surgery times will converge to some limit, and I won't be able to extend the flow past that limiting time. But Perelman showed that if we just choose delta small enough, this won't be the case. So we will really be able to construct this Ricci flow with surgery, which will, be defined for all positive times. We won't be running into some accumulation point of times. All right, sorry, are there any questions? Okay, so let me just discuss briefly, even though this won't be exactly the purpose of this talk, how this Ricci flow with surgery was used by Perelman to deduce the important topological conjectures. So first of all, if the flow goes, so there are basically two cases if we construct such a Ricci flow with surgery. In the first case, we say that the flow goes extinct, and that is the case that occurs when eventually all these components here look spherical or look like S2 cross S1s. And so they basically all are being discarded in, after a while by a surgery process. So essentially, if somehow the flow is empty, if somehow at some time the time slice is empty, then we say that the flow goes extinct. And we know that we've thrown away time slices that look either like quotients of spheres or like they look like S2 cross S1. Okay? And then in this case, we know that the initial manifold was a connected sum of these components that we've thrown away. Okay? So we have a topological description of the initial manifold just by taking a connected sum of these guys. And so this led Perelman to deduce the Poincaré conjecture, stating that if you have a simply connected 3 manifold, then we are diffeomorphic to S3. Okay? And the way this proof goes is that Perelman came up with the reason why in the simply connected case, the flow has to go extinct in finite time. Then he could deduce that M has to be diffeomorphic to a manifold of this form. And then, well, then we use simply connectedness to rule out all cases except for the S3 case. In the other case, what could also happen is that the flow exists for all times. Okay? And so we may be performing surgeries every second or something like this, but somehow the flow never, the manifold never disappears. And in this case, Perelman could show that we can separate the manifold into what is called a thick part and a thin part for large times. And on the thick part, the metric converges to a hyperbolic metric, while on the thin part, it collapses along certain fibers, S1, T2, and S2 fibers with some lower curvature bounds. Okay, so this part is relatively technical, and I just want to give you some brief overview. Okay? So by analyzing this thin part further, it was then possible to deduce the geometrization conjecture, which essentially stated that we can cut every 3 manifold along embedded and incompressible copies of S2 and T2 into pieces which admit a homogeneous geometry. Okay? So just in a nutshell, this is how the Ricci flow was used. So in the finite time extinction case, we would more or less get the Poincaré conjecture. And in the infinite, like in the immortal case where the flow exists for all times, we would somehow see the other geometric pieces. All right, so I assume that I have until, what is it? I have 7 more minutes. But yeah, please correct me if I don't. What is it?
I said yes.
Oh, so, okay, great. Thanks. Yeah. So sorry. Okay, so this flow was very useful, and it seems like a very powerful tool. But so the flow, this Ricci flow with surgery, did have one drawback, and the drawback is that the surgery process has to somehow be performed by hand, and we have to make certain, and it's not canonical. That means we have to make certain choices whenever we perform a surgery. And that doesn't seem to be a canonical choice option for some of these choices. So for example, in order to perform a surgery, we have to choose some small surgery scale delta. And delta just has to be small and positive. And there's just no canonical number that's both small and positive. Also, the location of these surgeries has to be chosen by hand. And there's also no canonical way of specifying where exactly we have to perform the surgery. So if we cut, here or here. And even worse, let's say we performed some Ricci flow with surgery, but then we would go back and say, well, we would want to perform the first surgery differently. Then if we performed a different surgery at time T1, then this could lead to potentially a completely different type of evolution of the Ricci flow with surgery with different options that we have for surgery parameters and so on. So it's a mess. You would basically, given a single initial condition, we would have a whole tree of different Ricci flows with surgery starting from this. And so this was also recognized by Perelman in both of his papers. So for example, in his first paper, he wrote it is likely that one would get a canonically defined Ricci flow through singularities, but at the moment I don't have a proof of that. Okay. Okay, so this concludes my first part, and I'm running a bit behind on time, but I think that's probably good. So let me just use the next 5 minutes to give you a brief outlook into somehow the next chapter. Yeah. So what I want to do now is so you know, or what I should say, what I did previously is I basically gave you a background on Perelman's work on Ricci flow with surgery, and how this was used in the geometrization and Poincaré conjectures. So what I want to do next is I want to talk about more recent development, especially development addressing this question of Perelman. And then I will be able to state the main uniqueness result, maybe in the next lecture. Okay, so essentially what I want to get at in this chapter is I want to show you that Perelman's conjecture or Perelman's question can be answered in an affirmative way. Okay? So this is maybe a more accurate description here. So more or less what I'll try to convince you is that there's some kind of reasonable definition of weak Ricci flows that somehow flow through singularities, so where they somehow automatically do the surgeries, or somehow they flow through singularities. We don't have to perform any surgery by hand. Okay, so they somehow seem to be more canonical. And then within this class, we have existence and uniqueness. Okay? So given initial condition, there is exactly one such flow that flows through singularities. And I'll spend the remainder of this chapter telling you what this flow is, and then I'll state the main uniqueness result. But just for the people here who maybe work on mean curvature flow, let me just compare the situation that we're in with the mean curvature flow situation, because I think this analogy will be quite useful. Okay? So in mean curvature flow, well, mean curvature flow concerns the evolution of embedded hypersurfaces often in Euclidean space. So it's kind of a cousin of the Ricci flow. And the pictures that we would draw, they would be very similar to what I've drawn before. So we would also see neck pinches and so on. And we could ask, similarly, are there some weak flows that somehow automatically flow through singularities in mean curvature flow? And the answer here is a clear yes. So there are two flows. They're called the level set flow and the Brachy flow. And they exist, they can be defined because in mean curvature flow, mean curvature flow, there's some ambient space, and basically the ambient space can be used to define singular points and so on and so forth. So so for example, for the level set flow, we can define a weak flow through some viscosity principle or comparison principle, and we can define the Brachy flow by some weak principle. However, if you look at general mean curvature flows, it's not hard to show that these flows exist. So that somehow almost follows from the definition, especially for the level set flow. However, for the general case, then let me focus on the level set flow. There's a phenomenon called fattening, which will show us that time slices will suddenly become n+1 dimensional. Okay? And essentially, this is associated to a non-uniqueness phenomenon. Okay, so essentially these level set flows are not the flows that we should be looking at, and so this more or less implies that the corresponding Brachy flows are non-unique. Okay? So this theorem that I wrote up there is really false for general mean curvature flows, even in dimension 2. However, if we look at a more restrictive class of mean curvature flows, namely the mean convex mean curvature flows, then it was proven by Brian White that there we have non-fattening, and so essentially we have uniqueness of the corresponding Brachy flow. And then even better, if we're looking at the two convex mean curvature flows, then we have uniqueness. We still have the uniqueness because they're mean convex, and we can write down then we can write down mean curvature flows with surgery. So basically there's a similar construction of mean curvature flow with surgery. Again, the picture would be almost the same that I've showed you before. And these weak flows, they arise as limits of mean curvature flows with surgery as the surgery scale goes to 0. Okay? And so this is somehow the idea, and this is the only way why I've done this digression. So I'm sorry if you're not an expert on mean curvature flows. the only reason why I want to give you this digression here is to show that we want to somehow adapt this idea. So the idea of defining these new Ricci flows of singularities will be essentially the following, and I'll describe this in more detail in the next class. So what we want to do is we want to take a sequence of Ricci flows with surgery, starting from the same initial condition for smaller and smaller surgery scale. And then we hope that as the surgery scale goes to 0, that we converge to some nicer, more canonical Ricci flow through singularities in the limit. Okay, so just to avoid misunderstandings here, Ricci flow with surgery is given by a sequence of Ricci flows. And now we want to look at a sequence of Ricci flows with surgery and let them converge to some limiting kind of object. Okay, so we're going to look at a sequence of sequences. All right, so I'm going to explain this in more detail on the next slide. So don't worry if somehow this was, if you didn't get the mean curvature flow references here. And I'll state these, I'll discuss more precisely how these, what these weak Ricci flows through singularities are, how they are constructed, and then I'll state the main uniqueness results and talk about their proof tomorrow. All right. Thank you. Thank you for your attention, and I'll hope to see you again tomorrow.
Thank you, Richard. Are there any quick questions? Okay, if this is not the case, we thank you again, and we meet again tomorrow, if I remember well. Yes.
Okay, great. Thanks.
Same time. Same time,
I think. Yeah.
Thanks a lot for this very nice presentation.
Thanks. Yeah, and have a good evening. Yeah.